But my name is Scott Hamilton with the University of Missouri Science and Technology, and we are here today to talk a little bit about our cluster because we've got a little bit of bragging rights with some of the proof of concept that I've done. And I'm glad to see Dr. Dawes here because it's your code that I'm actually showing we're able to beat Titan with. Titan's the second fastest supercomputer in the world, but as very few people realize, the metrics that they use to do that actually make it fairly easy to outperform. So just get started. I'm going to go over a little bit of the history of high-performance computing, some of the common metrics used to rate high-performance computers, what some of the current trends are, what we can do to fix this rating system, and also stepping forward in how we can achieve exascale computing. A little bit of history. The very first supercomputer was in 1964, the CDC 6600. It ran at a whopping 10 megahertz. You've got more processing power in your cell phone right now. But that took several iterations. You see there's about 10-year gaps in between the big jumps in high-performance computing. The next big jump actually happened in 1993 with the Paragon supercomputer. It was the first MPI-based supercomputer. All the ones prior to that was what you would refer to as a shared memory system. And that is where all the processors and all the RAM set in one box, kind of like we're all in this same room together now. If we were trying to work a jigsaw puzzle together, we'd all have access to all the pieces. Paragon was a big paradigm shift in computing to a distributed memory system. That would be like me bringing in a 1,000-piece puzzle, saying, everybody come here, grab a handful of pieces, now go to a different room. So as soon as you needed another piece to the puzzle, you had to communicate with somebody to get it. So it brought a whole new paradigm shift into computing. And you'll see that at that point, we started making leaps and bounds in performance. And that is because as soon as they figured out this whole distributed memory and message passing and sharing information between compute nodes, all of a sudden it didn't have to fit in one box anymore. So you could get massive speed up by just adding more hardware to the problem set. And that's exactly what the trend has been over the last several years of supercomputing up to the current top performing supercomputer, the Milky Way 2, at a whopping 54,000 teraflops. We're getting into near the petaflop range there. The interesting thing is this chart is entirely based off of LINPACK, which I'll get into a little bit later. You can see that here's the growth trend, and it has been a pretty steady, constant line. That line's still following that same trend. The scary part is something has to change drastically if we want to get to the next stage of exascale computing. Right now, our common metrics are petaflops, teraflops, gigaflops, all based off floating point operations. A teraflop is, or a petaflop is, well, it's 1,000 trillion. I don't know what that number is right off the top of my head, but each one of those iterations is 1,000 flops or floating point operations. Each one's 1,000 times bigger than the one below it. Exascale is where we're headed next, which is 1,000 petaflops. And those common metrics really don't tell us the true performance picture of a cluster. So our current trends top 500 list is generated by LINPACK. It's dominated by control flow-based systems. LINPACK is a very simple linear algebra solving large matrices of linear equations. Doesn't take a lot of takes a lot of inter-process communications, but not a lot of file I/O or file storage. And if any of you are into scientific modeling at all, you find out very quickly that LINPACK is not a very good performance indicator for a cluster because your models and simulations require a lot of file I/O. And so what happens is they get 80 to 90% efficiency on LINPACK, but only about 5% efficiency when you start doing the real-world problem. They designed their cluster to get on this list. They didn't design their cluster to solve a real-world situation. As you can see, we require more than just flops. We require custom data flow architectures, and some of the examples of speed up if you custom design your data flow is with the gigabytes of data in the banking system. When they custom designed the data flow, they saw 30 times speed up on a single system. Not just, yeah, they could have thrown more processors at it, but they would have seen the same amount of speed up as architecting their software for their data structures. You get into geophysics, you get terabyte sizes of data sets, and once again, when they redesigned the data flow, they were seeing 70 times speed up in performance, and it all came down to designing the system for optimal data performance. And then the petroleum industry, we have some guys running some petroleum-based software on our cluster here as well, and they're seeing the 200 times speed up by re-architecting the data infrastructure. So basically, I have a few examples of how we fix the performance issues here on our campus. The one I'm going to primarily focus on is the quantum chemistry, but we've also done some work with rock mechanics, nuclear engineering, aerodynamics, and neural networks. Each one of those problems has a different solution to improving the performance on a cluster. The quantum chemistry needs a lot of file I/O because it writes very large scratch files in the tens and hundreds of gigabytes before it even starts its simulation. So you can see the bottleneck there becomes very rapidly your I/O rates on your hard drive. The rock mechanics, on the other hand, is very memory intensive. It requires a lot of RAM on the system, does a lot of matrix calculations, can be improved greatly by using the new accelerator chips, the CUDA technologies, which we also have on our campus. Nuclear engineering is much the same way, so is the aerodynamics. Those three fit very well together. And then the neural networks requires a lot of communication bandwidth between processes and processors. So this is basically a model of the energy levels between molecules and a chemical compound. I don't know a whole lot about it. I don't really know what the chart means myself, but it's worthy of a good picture to just show this is the end result of what we're actually calculating with the quantum chemistry. And it is the interaction of the bonds and the way the atoms within a molecule interact with each other. And there's a lot of intense mathematics that go into that model. And just real quick here, some final system performance numbers that we ran when we were initially doing solving the quantum chemistry problem. You can see this line here was with, wish my slide was a little bit more readable, but basically we have four drives in RAID and 6 drives in RAID 0. And we also compared that to SSD drives. We found out that 6 drives in RAID 0, just conventional 15,000 RPM drives, actually outperformed our SSDs, which are like the fastest drives you can get now. We didn't really do any RAID tests with SSDs at the time because it was just too expensive. You put 6 SSDs in a system, and all of a sudden all your money went to hard drives. And we weren't seeing the performance benefit because the 6 RAID drives actually let us run on all 12 processor cores on the box without seeing too much of performance hit. So we didn't see an advantage going above and beyond. You can see here on this chart, it compares a Lustre-based system, which is a distributed file system, where we're storing the scratch files on a centralized repository versus using local disk cache on each machine in the cluster. And as you can see here, the blue line being local disk, when we ran 12 runs per node, you could see a steady increase as we added more processes to the cluster and just kept growing. On the Lustre system, we capped out, and that's a line at 40 gigabits per second data transfer rate, which is where our Lustre system runs today on our campus. We take it a step farther, and you see the little blue line down there, that's our current Lustre system on our campus. The green line is the Lustre-based file system on Titan back in April of 2013. It's actually the same file system they're using on the world's now fastest supercomputer, the Milky Way 2, uses that same file system as that little green line. And you can see, at least with the quantum chemistry problem we were running, our local disk with, you see the little red part with that yellow line that's going straight up. That's our current cluster. We have 748 processors with high-speed scratch. If we run that problem across all 748 processors, we're actually beating the fastest supercomputer in the world with performance with the quantum chemistry problem, because we're outdoing the file I/O bandwidth. Know that Dr. Dawes can attest to this. He's run this code on several supercomputers throughout the country and has not had successful runs before he came on board here. We custom designed the system to fit the problem. And the purple line here, that's the current file system on Titan, which you can see that they realized the file system was a big bottleneck. In April of this year, they upgraded the file system to a 1.2 petabyte per second transfer rate. And I went ahead and did the math and extrapolated out our line. And if we spend another $2 million on our cluster here on campus and put 70 more of our C-Series servers into the cluster, we would actually outperform Titan again. It would, like I said, it would be a cost of about $2 million. The thing to put all that into perspective is Titan is a $97 million cluster. So when it comes to solving a real-world problem, we have the know-how and knowledge here on this campus to exceed the top 500 supercomputers in the world. And earthquake data for shear wave splitting is one of the other things that we were doing. That one benefits greatly from local disk and local storage. It's a lot of local file I/O with really tiny files. Lustre doesn't like really tiny files. And I've been being told I've got about 5 minutes left. So we do propulsion, aerodynamics, jet wing simulations and modeling. 2 minutes. So in conclusion, the WinPack is a very poor performance metric because it doesn't take into consideration all the other requirements when it comes to solving real-world problems. And for data processing applications, the rate of producing results is a more logical measure. And one of the proposed solutions actually is to start making the supercomputer models include data generation rates as one of the metrics in the top 500 supercomputer list. So no longer is it fully based on just the flops or overall floating point operation performance of the cluster. And basically, several authors in ACM, as well as myself, will admit that the only way we're going to reach exascale computing in the near future is to start designing our software and hardware in conjunction with one another. That is our cluster design approach here on this campus. If you come to me and tell me you want to buy high-performance computing equipment on this campus, the first thing I'm going to do is ask, what are you going to use it for? Ask you for a sample of your code. We're going to find your bottlenecks, and we're going to design the system around it so that we get the peak performance in your bottleneck. And as a result, we hands down will always show higher performance than Titan or even Milky Way 2. We still beat Milky Way 2 because their file system is lax. And so right now with quantum chemistry, we have the fastest cluster in the world. And that's it. Does anyone have any questions?